All right, so let's start. Today you are going to learn a new chapter, chapter number 5, and here you are going to learn about uniform circular motion and gravitation. Okay, now by its name, so the name is uniform circular motion. So circular means if an object is traveling in a circular path, we call that object is in circular motion. Okay, so here in this picture you see that the object is moving in this circular path. Okay, so this is the circular path. So this is moving in a circular this object is moving in this circular path. That means the object is in circular motion. But what the uniform means? Uniform means the speed is constant. Speed is constant. Okay, speed or the magnitude of the velocity. As you know that velocity has, velocity is a vector quantity, so it has magnitude and direction, right? So when the object is in uniform circular motion, its speed is constant or the magnitude of the velocity is constant. Okay, so here you can see that the object is moving in this circular path in this picture, and the arrow, this green arrow shows the velocity vector. Okay, and you see that the length of this arrow, okay, is the same. So length same means the magnitude of the velocity or the speed are the same at point 1 and at point 2. Okay, but you see the directions are different. Here the direction is in this direction, here the direction is in this direction. Okay, and the direction of the velocity when it is in circular path is basically the tangent. Okay, so for example, if I want to draw the direction of velocity at that point, then it will be tangent to this point, and this is this. Okay, and so on. All right, so now you probably understand that circular motion means the object is in a circular, moving in a circular path, and uniform means the speed or the magnitude of the velocity is constant. Okay, but not the direction. Direction changes, and it is the tangent. Okay, now before we moving on, let me go to this simulation. Okay, all right. Okay, so if I start, you see that this object is in a circular path. Okay, it's in a circular motion. Okay, and you see that the speed of this object is 20 meter per second. So here you see the speed is 20 meter per second. Okay, so okay, so if I hit in the velocities, so it will show the direction of the velocity. Okay, so this velocity vector, this orange arrow basically showing you the direction and the magnitude of the velocity. So you see that as it is moving in the circular path, there is no change of the length of the arrow, but the direction changes always, and direction is the tangent at each point. Okay, now what I wanted to show here is this one. So here you see that it says that the acceleration is 7 meter per second square. Okay, meter second and second, that means meter per second square. So when it is moving in this circular path, there is some acceleration. But if you remember, the definition of the acceleration was this: delta v delta t, right? So that the rate of change of the velocity. Now we know that the velocity does not change. So velocity, it says that the speed is 20 meter per second, right? So here you see that the velocity is, the magnitude of the velocity is always the same. It is uniform circular motion. So delta v, if I write down explicitly this equation, it will be something like this, right? So no matter what is the delta t, you see that this is 20 meter per second, this is 20. So it looks like the acceleration is 0, right? From our definition, what we learned in chapter 2, right? But this simulation says that acceleration is 7 meter per second square. Okay, so what it means? So it means, although the we don't get the tangential acceleration. So tangential acceleration is the acceleration along the tangent of the circular path. We have some acceleration due to the change of the change of the direction. Okay, direction of velocity. Okay, because the velocity changes its direction, the acceleration we get here is basically due to the change of the direction of the velocity. Okay, so you see at each point the velocity is different than its previous point. Okay, so what is then the direction, and what is the relation between the velocity and the acceleration? Let me show you here. Okay, so if I hit acceleration here, you see the acceleration is to the center of the circle. Okay, so if I pause it, you see the direction of the acceleration is to the center of the circle. Okay, and along the radius. So you see this is to the center of the circle, right? At each point it is to the center of the circle and it is along the radius. Okay, so the acceleration what we get is not along the tangent. Okay, so in chapter 2 we learned this acceleration. Okay, so we learn this kind of acceleration, and we learn that the direction of the acceleration is either to the direction of the velocity or opposite to the direction of the velocity, depending on whether we are speeding up or slowing down. Okay, remember that. Now here we are getting another kind of acceleration. Okay, it's not to the direction of the velocity or opposite to the direction of the velocity, it's toward the center of the circle or circular path. Okay, so when we have acceleration due to the change of the direction of the velocity, the direction of the acceleration is to the center of the circular path. Okay, so because this acceleration is to the center of the circular path, we call it centripetal or radial acceleration. Okay, so and we use this symbol subscript r to represent that it is centripetal or radial acceleration. Okay, remember that centripetal acceleration or radial acceleration are the acceleration. This is due to the change of the direction of the velocity. Okay, and we use a subscript r to represent centripetal or radial acceleration. Okay, and the direction of the centripetal acceleration is to the center of the circle. All right, now let's try to find a relation between the centripetal acceleration and the velocity. Okay, so to do that, let's go back to our study guide. Okay, all right. All right, so this is our study guide. Now, in the simulation, we already show that the direction of the centripetal acceleration is to the center of the circle. Okay, and by using some vector addition and subtraction, or the tail to tip method that you will learn in chapter 3, you can also show that the direction of the centripetal acceleration is to the center. Okay, but it is a little bit difficult, so here I show it but I'm not going to talk about that because we already learned from the simulation that the direction of the acceleration is to the center of the circle or the circular path. Okay, if you are interested, go through this calculation. So here we use geometry and the vector algebra that you learn in chapter 3. Okay, and if you have question, you can email me, okay, or meet me during the office hour time. Okay, all right. So now so using the vector algebra, I mean the vector vector algebra, we can draw this thing. Okay, so here this r1 is the radius. Let's say at some point the object is here and this is initial position, this is final position. Okay, let's say to go from point 1 to point 2, let's say we need delta t time. Okay, now from here, this is the center. From the center we draw a vector. This is the radius vector at position 1, and the same thing, this is the radius vector at position 2. Okay, and you know that the radius, the magnitude of radius is same, right, of a circle. So although the direction, it looks like different, so you see the direction is this direction and the direction is this direction, but their magnitude will be the same. And let me call it r1 r2 equal to r. So when you use this symbol, I mean this absolute symbol, okay, so some quantity and then this absolute symbol, we call it absolute value. So absolute value of r means we are talking about the magnitude, okay, magnitude of a vector. Okay, so the magnitude of a vector r1 and r2 are the same, and that is the radius of this circular path. Okay, and you see that this r1 and r2 makes an angle delta theta. Okay, so this angle is delta theta. Okay, and now if I draw the velocity vector, so the velocity vector will be this one for position 1, and this one will be for position v2. Okay, now similar I mean let's take v1 and v2 here in this vector diagram. So you see that direction of v2 is this one, so we don't change it. Okay, and the direction of v1 was this one, right? Okay, so so here what I want to, I mean what I want you to understand is you see that v2, this v2 and this v2 are parallel, so I didn't change anything. So here for v1 I changed little bit. Okay, so v1 direction is this one. Okay, but in this picture, in this triangle, I changed the direction of v1, okay, to this. Okay, so you see that this is the direction. So because I want to change the direction, so what I did, I instead of writing it v1, I wrote it minus v1. Okay, and you already learned that we can do that. Minus v1 means it is the same length of v1 but in the opposite direction, because v1's direction is this one, minus v1's direction is this one, right? So then use the tail to tip method. You can draw this line, right? So here you have one vector, the first vector. From the tip of the first vector you draw the second vector, and then tail to tip method tells us that the sum of these two vector is from here to here, from the tail of the first vector to the tip of the second vector. Okay, and we call it delta v. Okay, similar to delta r here. Okay, And then tail to tip method tells us that v2 minus v1 is equal to delta v, right? You know that here v2 is first vector, and then second vector is minus v1, and then the sum of these two vectors is delta v. Okay, so this is that equation. Now although I wrote v2 v1, but their magnitude is same. Okay, so they are different because they are not zero, because they are the vector quantities. Okay, now another thing here you have to understand is, because r1 is the radius vector at position 1 and r2 is the radius vector at position 2, and their corresponding velocities are v1 and v2. If r1 and r2 makes an angle delta theta, v2 and v1 will also make the same angle. So that's why you see that the angle between v1 and v2 is delta theta. Okay, now you see that this triangle and this triangle looks like a similar triangle. Okay, so because they're similar triangle, we can use the similarity of these two triangles to write this equation. Okay, so delta v over one of the vector v, similar, I mean this is for this triangle, and for this triangle we can write delta r by r. Okay, so here v is the speed and r is the radius. Okay, so this is basically from geometry. When we have two similar triangles, we can write something like this. So if we understand this, okay, the next step is easy. Now the next step is I want to I want to divide this with respect to delta t. So I want to, okay, so we have this equation and I want to divide this quantity by delta t. So let me write down this. Okay, and the same thing for this one. Okay, so I can write delta v delta t, right? And here I can write delta r delta t, right? Little bit, I simplify a little bit. Then what I have here is delta v delta t is here basically the acceleration, and this acceleration is this a subscript r. Okay, and here delta r delta t, the rate of change of the radius vector is the velocity. Okay, so if I multiply both sides by v, this v will cancel out, so I will have ar in the left hand side, and on the right hand side I have v square over r. So the definition, the mathematical definition of the centripetal acceleration is this one. Okay, centripetal acceleration is equal to v square over the radius vector. Okay, all right. Okay, so the derivation I have already in this slide, so try to understand and let me know if you have question. All right, so here you see that this is the definition, mathematical definition of centripetal acceleration or the radial acceleration. All right, let's move on. Okay, so as you already know that the direction of the centripetal acceleration is to the center or along the radius, so that's why we call it centripetal acceleration or radial acceleration. Okay, and we use ar to represent centripetal or radial acceleration. In some textbook or in some lecture note, you will see that people also use this symbol, okay, a subscript c, to represent centripetal acceleration. Okay, c means centripetal, because the textbook I am using, we are using they use r as a subscript, so I'm using the same thing. Okay, AR means radial or centripetal acceleration. But if you see somewhere that people use a subscript c, that means it is the same thing, the centripetal acceleration. All right, so few more terminologies we need to understand. The first thing is the frequency and the time period and their relation with the velocity. Okay, so let's try to understand this. Okay, so what is the frequency? By the way, to represent frequency, we use f, small f, to represent frequency. Okay, don't confuse force and frequency. Force is the capital F, and frequency is the small f. Okay, lowercase f. So what is the frequency then? Frequency is the number of full turns. Okay, number of full turns per second. Okay, so because in uniform circular motion, the object is moving in a circular path. Okay, so frequency means in 1 second how many times it travels. How many full turns it covers in 1 second. Okay, so if it covers or if it travels 5 times, then the frequency is 5. If it travels 2000 times, for example, it will be 2000. Okay, so in 1 second, the frequency means how many turns in 1 second. Okay, so remember that. And the standard international unit is revolution per second or hertz. Okay, it's basically the same thing, both used. It's turn per second or rev per second or hertz. Okay, so that is the frequency. And the time period we use capital T to represent time period, and time period means the time to travel 1 full turn. Okay, so frequency means how many turns in 1 second, and time period means the time for 1 full turn, 1 full revolution. Okay, so if an object starts from here, it travels all the way to this circle and come back this point. The time it takes to do that is the time period. Okay, so the time period is the time for 1 full turn. On the other hand, the frequency is the number of turns in 1 second. Okay, they are very close, but not it means they are same, but they are not exactly the same, but they are related. Okay, and how they are related? They are related by this equation. Time period is equal to 1 over frequency, or frequency is equal to 1 over time period. Okay, so the both are correct. And because the time period means the time, so its standard international unit is second. Okay, all right. Now let's try to understand the relationship between the time period, frequency, and the velocity in an uniform circular motion. Okay, so to do that, let's recall that the definition of speed is the distance traveled divided by the travel time, right? In chapter 2, you already learned this. Speed is equal to the distance traveled by an object, and divided by the time it needs to cover that distance. Okay, so distance divided by time. So in a uniform circular motion, okay, so if an object starts here, okay, so let's say this is the starting point. Now we already know that to cover 1 full turn, that means if it starts from here, okay, and stops here, okay, so if it goes in this direction and come back to this point, okay, the time it needs is equal to the time period, right? So here in this equation, we already know for 1 full turn it needs this time equal to the time period, right? But what is the distance from here to here? What is this distance? So if this radius is r, okay, so then this distance is the circumference of this circle. Okay, and the circumference of this circle is, if you remember from the geometry class or the math class, it should be 2 pi times radius. Okay, so the distance it covers is 2 pi r. Okay, so you see that. And now you already know that 1 over t is the frequency, right? So I can write this. So you see the relation between the speed and time period is this one. Okay, and relationship between the speed and frequency is this one. Okay, so we'll be using these equations when we solve some problems. Okay, so these two relation gives us the relationship between the speed and the time period, or the speed and the frequency. Okay. All right, so let's move on. The next thing is the centripetal force. Okay, so earlier in chapter 4 you learn about that the force and acceleration are related, right? You see that the Newton's second law of motion tells us that force is equal to the mass times the acceleration, right? So that's the Newton's second law. So now here we see that there is an acceleration AR, right? So there should be some force to the center of the circular path. So this equation tells us that the direction of the force, the direction of the acceleration is to the direction of the force. Okay, that means the direction of force and the direction of the accelerations are same in Newton's second law, right? So now we see that we have a new acceleration that is to the center of the circular path. So we should have a new force whose direction should be toward the center of the circular path. Okay, so because we have now new acceleration, we should have a corresponding force, and this force we call the centripetal force. Okay, so when an object is in uniform circular motion, we have a force whose direction is to the center of the circular path. Okay, and we call it centripetal force or the radial force. Okay, similar to the acceleration, we use subscript r to represent it is a centripetal force. Okay, or radial force. And what is the relationship between the centripetal force and centripetal acceleration? Is basically the same as the Newton's second law. We just change the subscript. Okay, so Fr equal to MAR, that we already know, right? And because AR is V square over R, we can substitute this, and the centripetal force is basically this equation. The mathematically we can represent the centripetal force by this equation, mv square over r. Okay, now it's not a special force, it's basically the sum of the force, it's the net force whose directions is toward the center, center of the circular path. Okay, it could be the tension force. So for example, here in this picture, so when you tie a small mass in a string and then try to rotate in a circular path, so this force is basically the tension force. Okay, so this tension force is basically here is the centripetal force. Okay, so the the centripetal force is not a special kind of force. It is the net force whose direction is toward the center of the circular path. For example, in this picture, it is the tension. So tension here is the centripetal force. Okay, the gravity could be the centripetal force sometime. Okay, we will see some example. In some time, we will see that the static friction is the centripetal force. Okay, so remember that centripetal force is not a special kind of force. It's a net force whose direction is to the center of the circular path. Okay, all right. Now let's say you are rotating this one in this circular path, and if some point if this string breaks, what happened? If the string breaks, I mean if the string if the string breaks, okay, it will follow this tangent path. The object will follow this tangent. Okay, the object will no longer be in this circular path, it will follow this direction. Okay, so here in the next slide you can see that. So here you see that the string breaks. Okay, and then you see the direction of the motion of the ball when the string breaks, so it will follow this direction. Okay, all right. So let's see a simulation. So here in this picture you can also see that some of the spark are no longer in a circular uh, motion, they follow this path. Okay, because they loses the centripetal force. Okay, because they loses the centripetal force, so they follow the tangential path. Okay, let me show at least one interesting simulation. I think I have two. All right, so let's try to okay, so let me use this one. So Earth and satellite. Okay, now we'll be learning this in the next lecture in details, how satellite orbits around our planet, but for the time being, let me start with that. The satellite orbits around our planet in a circular path, and gravity actually supply this force. So here, when satellite orbits around our planet, or for example our planet is orbiting around the sun, it's basically the centripetal the gravity between the satellite and the gravitational force between the satellite and the planet basically supplies the centripetal force. You know that to keep something in a circular path we need a centripetal force. So you see that if I start this, you see that is that is moving in a traveling in a circular path. You see the satellite's path is a circular, so it is in a circular motion. And for simplicity, let's assume that the the motion is uniform circular motion. Okay, so although it's not uniform circular motion, and I mean in real life it is not exactly circular, it's elliptical, but in this model it is circular. So, and it is uniform circular motion. Okay, so because it is uniform circular motion, okay, the speed is constant in this path, and also because the speed is constant and it is in uniform circular motion, there is a there is a centripetal acceleration. Okay, and there is a centripetal force. Okay, and who supply this centripetal force? So in this case, okay, for the satellite and planet, it's the gravity. So you see that the gravitational force is to the center. Okay, so you see that the satellite, so here you see that, let me pause it. So you see that let me redo it. Okay, so here you see that the gravity is the direction of the, okay, so let me pause here and then use this. Okay, so here you see, okay, let me use another color. So here you see that this is the direction of the force. Okay, so this is the centripetal force. Okay, this centripetal force is supplied by the gravitational force here. So although we did not learn about gravitational force between the satellite and the planet, okay, which we are going to learn in the next lecture, but just, I mean, just try to just try to just assume that there is a force, and this force is basically the gravitational force. Okay, and this gravitational force supplies the centripetal force, and because of the centripetal force, the satellite is in this circular path. Now, the thing I wanted to show is what happened if there is no centripetal force. What happened if somehow I turn off the gravity? Okay, so if there is no gravity between the satellite and the planet, what happened? Okay, so here you see that I have the option to turn on and off the gravity. So if I turn off the gravity somehow, what happened? Let's see. Okay, so you see that it follows the tangent. Okay, so if there is no gravity, if there is no centripetal force, okay, it follows the tangential path. So that I wanted to show you. So we'll be learning about gravity and gravitational force in details in the next lecture. Here, the thing I wanted to show is if there is no centripetal force, it follows the tangential path. Okay, all right. All right, so another simulation I want to show before move on. So this one. Okay, so this is actually a racing track. Okay, so you see that racing track has some circular portion. So this is the circular portion and this is the circular portion. Okay, so when you drive, you see that all the highway turn, okay, all the turns basically, the turn are basically part of a circular path. Okay, so when you drive through a circular portion of a street or a highway, you have to, someone has to provide some centripetal force, okay, to keep your car in the track. Okay, if there is no centripetal force, it will skid away. Okay, so first let's see here what happened. So let me animate it and then show the vectors. Okay, now if I show the vector, so you see when it is in the circular portion, you see that there is a circular, there is a centripetal acceleration to the center. Okay, to the center of the circular portion, and the forces direction is also to the center. Okay, so who provides this centripetal force in this case? Okay, so so let's say here, okay, so when the car is in a circular portion of the track, you see that we have centripetal force. Okay, so this, the direction of the centripetal force is to the center, and this is the centripetal acceleration. But the question is, who provides or supplies this centripetal force? Okay, so we see that there is a centripetal force, to keep our car in this circular path, in this portion of the circular path. Okay, someone needs to provide some centripetal force, okay, so that the car is in the track. If there is no centripetal force, it will follow this. Okay, it will skid away. Okay, but the question is, who provide this? So in this case, in a highway track, okay, static friction basically provides centripetal force. So that this force is basically the static friction between the car tires and the ground. Okay, car tires and the ground basically provides, and the static friction between the car tires and the ground basically provides the centripetal force. Okay, so we'll be doing some problem later. Okay, and there are two types of highway curve. Okay, so in the next slide we are going to learn details about that. But yeah, the thing I wanted to show here is in our everyday life, okay, we encounter the circular motion almost every day. Okay, so when we drive, okay, I mean, we have to cross some circular portion of the highway or the street, right? So that time, okay, someone needs to provide a centripetal force, and that centripetal force is provided by the friction force between the car tires and the ground and the street. Okay, so if there is no static friction, the car will not be in the track. Okay, so yeah, it will skid away. All right, and you know that during rainy day um, or snowy day, okay, you know that the coefficient of static friction of a snowy route and a rainy route is less than sorry is less than a regular dry day. Okay, so that means the static friction force in rainy day or in snowy day is less. So we have to be careful when we drive in a rainy day or a snowy day. Okay, because the static friction between the car tires and the road decrease in a snowy day. Okay, because of this. Okay, so you know that the static friction is defined as this. Okay, normally in this chapter, this normal force, this is the normal force, right? And this normal force is basically equal to the car's gravitational force or the weight. Now dry day, in a dry day, mu s is I mean high normally uh, at this order, okay, 0.6. Okay, but in a snowy day it becomes something like this, 0.15 is much less. Okay, so when the coefficient of the static friction is much less, okay, you know that the static friction also decreases. Okay, so when it decreases, there may not be um, enough static friction between the car tire and the street. Okay, so that's why during the rainy day or snowy day we have to be careful when we drive, and especially when you encounter a highway curve. Okay, all right, so let's go back to the study guide. So few more things I want to tell you. So highway curve, actually this is the last thing I'm going to teach today. Okay, so there are two types of highway curve. Okay, one is banked, one is unbanked. Okay, so unbanked is basically flat. Okay, so when the road is flat, we call it unbanked. Okay, the term we use is called unbanked. And when the route is something like this, something like this, okay, we call it unbanked. Okay, so for example, this is an example of unbanked. In unbanked, so in unbanked turn, you see that this side, I mean, if I make a cross section, it looks like this. So the outer side is raised little bit compared to the inner side. Okay, so if we have some highway turn, something like this, it's called banked turn. Okay, so this is banked turn. Okay, and the flat, if it is flat, we call it unbanked. Okay, so normally nowadays all the turn or most of the turn is banked turn. Okay, most of the turn in a highway is something like this. Okay, it has some advantage, so we are going to learn that. But first, let's try to learn the mathematics of unbanked or flat turn. Okay, okay. In fact, we already learned. I already mentioned in the simulation. Okay, so this example is, it looks like it's unbanked. Okay, it looks like a flat turn. Okay, so in flat turn, the only thing we need to understand is to keep the car in this circular portion of the path. Okay, the static friction between the car tire and the ground needs to provide the needs to work as a centripetal force. Okay, now what is the centripetal force? The direction of this direction of the centripetal force is in this direction. The direction of the static friction should be in this direction, and the static friction definition, mathematical definition, is this. Okay, so if you know the coefficient of the static friction, if you know the car's mass, if you know the gravitational acceleration, you can immediately determine what is the static friction. And then you see that this is related to this equation, right? Sorry, it's not. This is related to this equation, right? And this equation is basically mv squared over r. Okay, so the left hand side, this fr is basically the static friction. Okay, on the other hand, the right hand side is this one. Okay, so when you drive in an unbanked curve, unbanked highway turn, you see that speed is a factor. Okay, so speed, so during rainy day, because this is less, or snowy day because this is less, the speed needs to be less. Okay, so that's why um, we need to drive slowly in a rainy day or in a snowy day. Okay, because you see that there is a relation between the force, the coefficient of static friction force and the velocity. I mean the magnitude of the velocity or the speed. Okay, so remember that it may be helpful when you drive in. I mean when you really drive in a snowy day or in a rainy day. Okay, especially when you encounter a turn. Okay, all right, so unbanked turn is easy to understand. The two things you need to understand is the static friction. Static friction is basically the component that is supplying the centripetal force. Okay, so if there is no static friction or less static friction, it will be problematic. Okay, and another thing you need to understand is the centripetal force. The definition of centripetal force is this, and the definition of the static friction is this. By combining these two, we can solve any unbanked highway turn problem. Okay, so we'll see some in problem solving lecture. Okay, and the last thing I want to tell you is the banked highway turn. Okay, so banked, as you already know, means outer edge. Banked means outer edge of the road is slightly raised to avoid skidding. Okay, so it's something like this. You see that. Okay, nowadays most of the highway turn are banked. Okay, okay, now what is the advantage that I'm going to show you? Okay, so here is one of the example of the banked highway turn. Now to understand the physics behind the banked turn, let's consider this slice. Okay, let's consider this slice of the banked turn. Okay, and let's say the car is somewhere here. Okay, so this is the car. The next thing to understand the physics, we have to draw the free body diagram. Okay, and in chapter 4 you already learned the free body diagram. Okay, so although it looks like a inclined plane, okay, but we are not using we are not going to modify our the coordinate system. So normally the coordinate system is this, and for inclined plane in chapter 4 we modify our coordinate system, right? In chapter 4 for inclined plane, if you remember, the the coordinate system was something like this or this. Okay, but here when you do the banked turn problem, do not modify the coordinate system. Okay, all right. So what it means, it means our y-axis is this, x-axis is this, it's regular x and y-axis. Okay, now what forces we have here? So because the car is here, we should have gravitational force in this direction. So this is the gravitational force direction, and this is the normal forces direction. Okay, so this is the normal forces direction. Okay, so these are the two forces we have basically. Yeah, we can we should also have the static friction. Okay, but for the time being, when we solve the banked highway turn, we are neglecting the static friction for some reason, and let me tell you why. And that is basically the advantage of the banked turn. Okay, so there is a static friction between the car tires and the ground, but we are neglecting it. Okay, why we are neglecting it? Because there is already some forces to the center of the circular path. So you know that to keep the definition is to keep something in a circular path, we need, I mean, someone needs to supply some force, okay, that is to the center of the circular path. So here, even if we don't have the static friction, you see that a component, so you see that this component has, I mean, this force has component to the center. Okay, so here you see, so here you see that the direction of mg is to the y direction. So this is our y, so you see that this is negative y. Okay, now this is no longer along y and x, right? So we have to break it. So x direction is this one, and you see that it is neither along the x-axis nor along the y-axis, right? So we have to break it, as we already learned, right? So because it is no longer along x and y, we have to break it. And if this angle is theta, by using geometry you can show that this angle is also theta, and then you can break it into its adjacent component. Adjacent component is fn cosine theta, and this is the opposite component, it is the fn sine theta. So you see that this is opposite, and this basically the same thing. So you see that even there is no static friction, there is some component of the normal force which is to the center of the circular path, and because of this component, because of this value, the car stays in the circular path. Okay, so even there is no static friction. So that's why if even in the snowy day, okay, it doesn't matter. Okay, even yeah, in the snowy day, if the carb is banked, it is safer than when the carb is unbanked. Okay, Yeah, and of course, I mean, if your speed is too high, um, it is problematic. Okay, there is some limit. Okay, but normally, because even there is no static friction, okay, if there, because there is a component that is to the center of the circular path, the banked highway turn is safer than unbanked. Okay, so we'll be doing some problem in next lecture, so I'm going to stop here. If you have question, let me know. Okay, so I'm going to stop today.